Welcome back. So just to recap from yesterday, we saw several examples of problems where we wanted to construct some sort of strange or counterintuitive object. And our method was we did 3 steps. First, we defined some kind of random object, like a random graph or a random coloring or a random set. And then we said, okay, let's define a random variable, x. And this random variable x always encoded the thing we cared about. We wanted to find some object that had no somethings. So we said x was the number of somethings in the object. Right? We wanted to show that it was possible x was 0, say, or possible that x was at least something or at most something. Then we calculated the expectation. And finally, we observed that so with positive probability, x is at least its expectation, or at most its expectation. Right? So we use this very simple recipe to construct these objects. And why was it easy to calculate the expectation? Because expectation has this amazing property the expectation of x plus y, expectation of x plus expectation of y. Expectation is linear, right? The average of something and the average of something else, the average of the sum is just the sum of the averages. Right? Very intuitive property. Well, why was this useful for us? Because all of our x's were like the sums over some possible s's of the indicator that s is has some random property. So s is in our random set or whatever, in whatever. So s is good for the random set. For the random object. Right? We were just counting the number of s's that had some property for the random object. And then using linearity, what do we get? The expectation of x is the sum over s of the expectation of the indicator function of this thing. Except what's the expectation of an indicator function? Indicator function is 0 or 1, so it's just the probability of the event. Right? So expectation of an indicator function is just the probability. Right? And then these things were always easy to calculate. Okay? So this was our basic recipe, and it worked very nicely for us. Okay, so let's just see one more example of that, where we have to choose a clever random object. And then we'll see some examples where this recipe doesn't quite work, and we have to do something a bit more complicated. Okay, so that's our plan for today. Oh, and please do continue to ask questions, ask more questions, right? The more questions you ask, then the easier it is for me to figure out what speed to go, which things I'm not saying. Okay. So it's always difficult to pitch a lesson when you're just reading people's faces and trying to interpret them. So the more you talk, the better. Okay, so here is a problem. I think it's maybe problem 6. Well, let's move up to 7, actually. So, alpha of g is the size, the max size of an independent set in a graph G. Okay, let's do a simple exercise first. Who can show me, that why is alpha at least n over the maximum degree plus 1? Delta is a max degree. Why is that true? How can you find an independent set in a graph of size number of vertices divided by maximum degree plus 1? Exactly. We can just do a greedy algorithm. We pick a vertex. This vertex v1 is going in our independent set. We've already decided. So therefore, we have to throw away all its neighbors. How many neighbors does it have? At most, delta g. Look in the rest of the world, pick any vertex at all, throw away its neighbors, and so on. Just continue until you run out of vertices, and you get this bound. Okay, extremely simple. So, here's a theorem, Uticado and Way, that improves this bound. Perhaps it's worth saying, if you replace the maximum degree here with the average degree, this is just Turan's theorem in disguise. So for those who don't know Turan's theorem, it tells you the maximum number of edges in a graph with no copy of kr for some r. Okay? For those who do, then you can think about why that's true. Okay? It's not immediately obvious. Anyway, here's an improvement. Alpha of g is at least the sum over vertices of 1 over the degree of v plus 1. Right? So this clearly improves this. If the graph were regular, it would be the same thing. But if the degree is very different, then actually we've got a much bigger independent set. Okay, how are we going to prove this? You might think, let's just do the same thing. As a general rule, mathematical rule, if you have a proof that does something and you want to strengthen, try the same proof again first. Okay, maybe it just works. Does it work? Pick a vertex, throw away the neighborhood, okay, that's some degree. So we're sort of throwing away each time the neighbors, the degrees of the vertices we picked. But that's only a small set. Why would that be the same as this sort of average over the number you throw away? This harmonic mean, I guess. Okay, it doesn't seem to work at all, right? Maybe we start picking vertices, and then we're stuck with the ones with really large degree at the end. Okay, any suggestions? Okay, let's follow our recipe. What is our random object going to be? What can we choose randomly? We're given a graph. So we could pick the vertex randomly. It's true. And that would throw away the average or something. But then we have to worry about what the degrees of these vertices are to decide then when you pick this one. Yeah, so this is a nice idea, and actually is an idea that works very well in certain settings, but unfortunately not so well here. If the graph were triangle-free, it would be a very good idea. So let's try something different. Okay, so we're given this graph. All we can do is choose the vertices randomly, right? We can choose the vertices in some random order. Okay, so let's choose a random order on the vertices. choose a random order of the vertices. Right? Instead of just picking the first one randomly and then the second one, let's just randomly order all of them. Okay. Now, what is our random variable x going to be? So we would like to find, we've got this random ordering, so we've got this sort of ordered graph. We want to find an independent set in this graph. Can you see how to find an independent set?
You can start at the first vertex and then remove all the adjacent from this order of vertices, and then do this for each sequential vertex until in the end you'll have a sequence with only vertex that.
Yeah, so I guess you're doing this from left to right. Yeah, yeah. So this is a good idea. I want to do something a little worse than that, but makes it a little easier to analyze. So instead of just throwing away vertices where you chose its vertex on the left, its neighbor on the left, basically what you're saying is you pick this guy and throw away this one. You pick this guy and throw away these two. This one's thrown away. This one's not thrown away, so you can choose it. Okay, I want to be stupid and not choose this one, because it has a neighbor to the left. Okay, I'm not going to choose this one, but I'm going to choose this one. No neighbors to the left, neighbor to the left, neighbor to the left. That's all I'm choosing. Okay, I was kind of done. I could have chosen more. But why are we happy with this? So I want to define x is the number of vertices with no neighbor to the left. Right? Which only sends edges right. So my idea is worse than yours, but why is it good enough? Yeah, because we're just happy with this. And why does it give, two things. We need to prove two things. One, why is this an independent set? If I pick all the vertices, yeah, right? If I pick all the vertices with no neighbor to the left, then you can't have an edge inside that set, right? Because the right-hand vertex would have a neighbor to the left. So this is an independent set. And what is the expectation of x? Well, it's the sum over vertices of the probability that V has no neighbor to the left. And what is the probability that V has no neighbor to the left? In a random permutation of the vertices. Exactly. V has to be the first one of itself and its neighbors. So it's exactly this. So this is exactly the expectation of x. So with positive probability, our x is at least the expectation, so there must exist an independent set of this size. Yeah. And we're done. Questions? Everyone happy? Great. Okay, so that's the last example I was hoping to do yesterday. This is our last example where you can just calculate expectation and are done. Okay, So the next example, that won't quite work. Or from now on, it won't quite work. Okay. But you see that even in this very simple case, sometimes you have to be a little bit clever with both choosing the random object and with choosing the random variable. Right? This choice is not always obvious. Sometimes it's kind of obvious, other times it's kind of clever. Okay. Okay. 8. Okay, so yesterday we defined the Ramsey numbers, R of k. In the morning talk, you saw them again in disguise. It's the smallest n, such that any red-blue coloring of the edges of the complete graph has a red kk or a blue kk, right? A monochromatic clique of size k. In general, or in more generality, we can define our lk to be the minimum n, such that every coloring of the edges of the complete graph in red and blue has a red KL or a blue KK. Right? So if L equals K, it's the same thing we saw yesterday. Right? Okay, so just to check we understand the definition, what is R1K equal to? Sorry, I can't hear you to shout.
You would, a red K1 is enough, so 1.
1, exactly. Very good. Thank you. Right, one vertex is already a red K1, just a vertex. There's no edges. Okay, so that was easy. What about R2K? K, right? Because if you have any red edge, you have a red K2. So all the edges must be blue. But if they're all blue, then K vertices is enough to get a blue KK. Okay, we're doing well. R3K. So now we want to avoid a red triangle or a large blue clique. Suddenly it's not so obvious what to do. Okay, so. Okay, what bounds can we prove? Okay, here's my bound, k, from below. R2k, yeah, so usually the upper bound, right? Yeah, so if you have k vertices, if any of the edges is red, that's already a red k2. So therefore, if you don't have that, every edge must be blue, but in that case you have a blue kk, if you have k vertices. Yeah. Okay, let's try and prove something from above. What can we prove from above? Okay, what can we, so we have our red graph is triangle free. What is a useful property of triangle-free graphs? Or what does it mean to be triangle-free? So I'm going to draw the red graph in white. Exactly. Right? The neighborhood has no edges in it. In other words, it's a blue clique. So if you don't have any blue clique of size k, this must have size strictly less than k. So now, how large a blue clique can you find? What have we just proved about the red graph? So we know it's triangle free, but using that we proved, this picture proves that every vertex has at most k neighbors, fewer than k neighbors. In other words, the red graph has maximum degree at most k. And we want to find a large blue clique, which is the same as a large No, sorry. Yeah, so it would follow from a large max degree, but what's it the same as in this graph? So G is the red graph, right? And the maximum degree is less than k. And we want to find a large blue clique. What is a blue clique in G? It's an independent set. We want to find a large independent set. We would like a lower bound on the independence number. What lower bound do we know on the independence number? Shout. Yeah, it's right here, right? It's still on the board. Right? The crucial lemma is still there. Delta of g plus 1 is at most k. So this is at least n over k. And we would like that to be at least k. And it is, if n is at least k squared. This is at most k squared. Okay? So this simple little lemma we just proved before actually was useful. Did it make sense? So what did we say? We took a triangle-free graph. We know that either it has a vertex of degree k or an independent set of size at least n over k. Great. Okay, so which of these two do we think is closer to the truth? Who votes k? Who votes k squared? Okay, so the k squared people, let's try and improve the lower bound. The k people can think about improving the upper bound, which is also an interesting question. Okay, let's try and come up with a coloring, say a graph, a triangle-free graph with no large independent set. Right? That's our task. How can you come up with, right, just to get, say, 100k, or something that's greater than k, right? Something 10 to infinity times k. We want to find a triangle-free graph with no independent set of size constant times n. How can we do that? So it's not very obvious. It's not obvious how to come up with a construction. Here's a construction that Erdős came up with in 1957 or something. So this was proved in 1935. And 20 years later, Erdős came up with the following construction. Here is the hypercube. 0, 1 to the, I'm not going to say, call it k. 0, 1 to the, let's call it n, whatever. Okay. It's a picture of the hypercube. I'm going to join each vertex to every vertex whose distance is greater than 2/3. I'm doing this correctly? I think I'm doing it correctly. So I'm going to claim this graph has no triangles, because if you change 2/3 of the coordinates from 0 to 1, and then change 2/3 more coordinates, and then change 2/3 more coordinates again, you can't get back to the beginning. So if you change two guys who are both in this layer cannot differ by 2/3 of the coordinates, right? They both have 1/3 the same, more than 1/3 the same as this guy. So there's no triangle in this graph. And it turns out, but it's not at all easy to prove, the largest independent set in this graph is exactly this guy here. All points inside what's called a Hamming ball of size n/3. This is proved by Kleitman in the, not sure exactly when. Okay? This gives some bound that's better than k, but not so much better. It's like k to the 1 plus epsilon. Okay, so that's kind of difficult result, and quite confusing. Go ahead.
I'm quite confused about this representation.
Oh, sure. Oh, sorry. Yeah, this is, say, this is 0, 0, 0. Or let's make this one 1, 1, 1, 1, 1. And 0, 0, 0. Yeah, this is a useful way of looking at the hypercube. And then, so in the bottom layer you have 0. In the next layer, you have all the things with exactly 1, 1. In the next layer, everyone with 2 1s, and so on. And you can draw it as a sort of a post set, right? So 1, 2, 1, 3, 2, 3. You can sort of, right, think as a graph going up as well. Sorry, but that's not the graph I'm using here. Okay, so this is some clever construction that gives something not so great. Let's try and beat it. Let's try to prove, as Edish did in 59, that this is bigger than basically k to the 3/2. Maybe there's a constant factor here, so I'll write this to mean I'm throwing away constant factors. Okay, so coming up with a particular construction was difficult. Let's not try to do that. Right? Let's do something easier. So what do we do with the diagonal Ramsey number, Rk? We just colored randomly. So why not try that? But we probably don't want to pick the red edges and the blue edges probably a half anymore. Right? Because now we only want a triangle versus a kk. We probably want a lot fewer red edges. Okay? So let's take a random coloring, but with many fewer red edges than blue edges. So what this leads us to is the definition of the Erdős-Rényi random graph. Which is also introduced in around the same time as this result. So what is it? What is the Erdős-Rényi random graph? This has been mentioned in lots of the talks and defined in some of them. How many of you were already familiar with GMP before this week? Okay, great. How many were not? Just say, okay, no problem. So let's talk about it. Good. So what is this object? It has n vertices, and for each edge, the probability that E is an edge of GMP equals P all independently. Okay, so just for each pair, you toss an independent coin. With probability P, it comes up heads, and you put the edge in. 1 minus P, you don't. Okay. So let us note that this is not a graph. Okay? So we tend to talk about it like a graph. I will also talk about it as if it were a graph. But we should always have in the back of our minds, we should remember, this is a probability distribution over all graphs. Okay, so we're just assigning a probability to each graph. Right? So the probability that GMP equals some particular graph H, some particular sort of labeled graph H, is just P to the E of H, 1 minus P to the n choose 2 minus E of H. Right? If we decide beforehand which are the edges and which are the non-edges, that's the probability that happens. Okay? That's all we're doing. Okay. So let's try to pick our red edges using this random graph. Okay. Idea. Let the red edges be GNP for some well-chosen function P of n. Okay? P is going to be a function of n. It's not going to be a constant. Okay? We'd like, maybe, the probability that GMP is triangle-free and the independence number of GMP is less than k, maybe that's positive. If we can choose a clever function P such that these two events both happen simultaneously with positive probability, then we'll be happy. Right? What will that mean? That will mean there must exist a graph with these two properties, and that's exactly what we want. Right? With n equals this guy. Right? What we want is that there exists a graph with n vertices, no triangle, independence number less than k. Right? That's our task. So if we can show it happens with positive probability, we're done. Everyone on board? Okay. So, spoiler, this is not going to work. But we'll see afterwards. We'll see. First, let's see how close we get, and then try to fix it. May I leave that there? I'll put this down there. Okay. So I don't like this and. This and is scary. It makes, we have like two events, each one is already a little bit scary. Intersect them, gets very scary. So let's try to separate them. So it would be enough, so sufficient to prove the probability that GMP is triangle free plus the probability the independence number is less than k is strictly greater than 1. Right? If you have two events and their probabilities add up to more than 1, then they must intersect. Right? You can't fit them both in the world disjointly. Okay. So just a quick aside. So I want to say that this was the event that Matthew was talking about on Monday. And this is sort of related to the event that Hoy was talking about this morning, except in random Cayley graphs rather than random graphs. Okay? So these are sort of things that do appear a lot in more advanced, these are sort of interesting objects to study in their own right. Okay. Okay, so we'd like to say, if we can prove that this to say has probability at least a half, and this has probability at least a half, then that'd be great. Let's try and pick a p so that both of them are reasonably likely to happen, then they must intersect. Okay. So hope, choose p such that both events have probability strictly greater than 1/2. Okay, so we need to try to understand these probabilities. How can we understand the probability that GMP contains no triangle? Okay, we already saw on Monday that this sometimes is a very difficult question, depending on exactly how large P is and exactly what question you're asking. But we have our standard recipe, so let's follow it and see where it takes us. So, suppose I'd just given you this question, which is on the example sheet, by the way. What would you say? What would you tell me to do? We have our random object, it's GMP. We care whether there are 0 triangles or not 0 triangles. So what is x? The number of triangles, right? And the natural x to take is the number of triangles in GMP. Right? And then the natural thing to do is to calculate expectation. Expectation of x equals what? Equals the sum over all triangles in the complete graph of the probability that that particular triangle is contained in GMP. Right? What is the probability that a particular triangle is contained in GMP? Each edge is present with probability p, all independently. So the probability is p squared, p cubed. Right? So for every triangle, the probability is p cubed. There are n choose 3 triangles, so it's just n choose 3 times p cubed. Right? Okay. Now, if we're likely to have a triangle, so if this is small, we can't really expect that we'd like to have a triangle, right? So we'd like this to be bigger than 1, say, right? If it's much smaller than 1, then the probability we have a triangle can't be very large, right? If you're very likely to have a triangle, your expectation is going to be at least a half or something, right? Okay, so it's at least a half. So what do we need for this to be true? This is like n cubed. We need p to be at least 1 over n. Sorry. Wrong way round. Wrong way round. I'm talking total nonsense. Sorry. Erase the last 15 seconds from your brains. I'm proving the wrong direction. We would like it to be likely you don't have a triangle. Right, sorry. So, what would be useful is if the expectation was small. Now, it's not necessary, as we'll come back to shortly, but it would be helpful. So let's say this should be at most 1, in which case p should be at most like 1 over n. Some constant over n. Okay, for us to have a good chance. Okay. Right. I guess I'm going to come over here. Oh, can I raise the definition of GMP? Are we happy with it? No one, unless someone complains, then I'm going to start erasing. No one is complaining. Okay. Okay. Okay, so this is the first thing that we would like for our P. If we're going to be triangle free, we'd like this to be true. Okay. What about the independence number? Okay, so again, if I'd just given you this problem, what would you say? We'd like to know if there are 0 or at least 1 independent sets of size k. So x should be exactly number of independent k sets in GMP. What is the expectation of that? I'll call it y, sorry, because we have an x over there. Yeah, to distinguish from that x. What is the expectation of this y? Yeah, so it's the sum. Let me do it slowly, still one more time. Sets of size k, probability S is independent, which equals n choose k choices for the set. What is the probability that there are no edges at all inside S? To the power k choose 2. Exactly, right? K choose 2. K choose 2 pairs inside, none of them can be edges. They're all chosen independently with probability p, so not there, probability 1 minus p. Okay. Okay. How large is this? Okay, I want to tell you a very simple but useful approximation, an inequality. One minus x is always at most e to the minus x for all positive x. What's the picture? Here is e to the minus x. And here is 1 minus x, except my... Yeah, sorry, my drawing is bad because the derivative at this point is actually minus 1, right? If you expand this out, you get 1 minus x plus big O x squared. Right? So close to 0, this is a very good approximation. Okay, with quadratic error. Oops, excuse me. Okay, and this is a very useful inequality for evaluating things like this. Okay, so whenever in combinatorics you see something like this, and the p is small, then you should approximate it like this. Okay, so what do we get? And here's another useful pair of inequalities I didn't use yesterday. This is also very useful. This thing is at least n over k to the k, right? Because it's n over k times n minus 1 over k times n minus 2 over k and so on, k minus 1. It's at most en over k to the k. Okay? These are things that are worth storing away somewhere in your memory. Okay? Okay. So anyway, let's use this as an approximation. So this is, what do we want? We want there not to be 1. There's en over k to the k times e to the minus p, k choose 2. Right? I just use these 2 upper bounds, very simple upper bounds that I just stated. Okay? Okay, how large is this? We have a factor of k that we can take out. En over k, e to the minus p, k minus 1 over 2 to the k. Okay, this is a bit confusing. When is this small? It's small if this e to the minus pk over 2 beats this n over k. Right? So this tends to 0 if n is at most e to the pk over 2. The same thing as k is at least 2 log n over p. Or sorry, what is p, right? P is at least 2 log n over k. So, here, to show that the graph is triangle-free, we wanted p to be smaller than 1 over n. Right? Here, to show that, so if the expectation of y, the number of independent k-sets, is small, then you're likely to not have any independent k-sets. So here we wanted this thing to be small, which means we want p to be bigger than log n over k. So we want p smaller than 1 over n and bigger than log n over k. So what should we choose p to be? How large is k? K is like n to the 2/3. So this failed badly. There's no such p. Right? So we want to choose this clever p so that you have, excuse me, no triangles and no large independent set. And we failed. Right? This was a terrible idea. We just wasted our time. Or did we? So, how do we fix this problem? So, I mean, yeah, the probability for red tells the probability for blue, right? So the problem is if our probability for red is too big, we're going to have triangles. And so I didn't prove it, but if p is bigger than 1 over n, you really are likely to have triangles. So on the exercise sheet, that's one of the exercises to prove it. Really, if p is like anything like large constant over n, you're going to have triangles. Similarly, this really is the size of the independence number of GMP, also on the example sheet, I think. Right? This is really what's happening. So there's no way to choose a P for which both these events are likely. Right? The triangles appear way before the independent sets of size k disappear. So the idea has to be perhaps a little more radical. Say it again, say it louder. Yes, we do not have to use GMP. Right? We tried, because that was the idea we had, but we're free to find any graph we like. And if there are few triangles, maybe we can just destroy them. We'll destroy them, though, in such a way that we don't increase the independence number. And your suggested way, which is actually a better idea than what we're going to do, was to switch the colors of some edges. The problem with that is it increases the independence number. You'll make more blue cliques. And while it's possible to deal with that, it's not easy. So let's do something simpler. A little more stupid, but a little easier to deal with. How should we destroy our triangles? We have a vertex, right? So it's a dumber thing to do, but it has the advantage, if you remove a vertex, your independence number does not go up. So whatever independence number we started with, we still have that afterwards. Okay. To do that, how many triangles do we need to have? How many triangles can we allow the graph to have? 5 or 10 is fine, right? But at what point does this argument break down? You're going to remove one vertex from each triangle, and you don't want to remove all the vertices. So let's make sure we have at most n over 2. Right? For at most n over 2 triangles, we can remove one vertex from each, destroy them all. We'll still have half the vertices, and our independence number will be no smaller. Will be no bigger, sorry. So we lose a constant factor, which we don't care about. Okay, so all we have to do is show that a suitable value of p, we don't have more than n over 2 triangles. How are we going to do that? Okay, that's what we want up here. So we gave up on this. Want x is at most n over 2 with high probability. Sorry, with high probability literally means with probability tending to 1 as n tends to infinity. You can just think of it as with probability close to 1. Excuse me. Okay. So, let me write this up here. Expectation of x is n choose 3 times p cubed. So, what we'd like is something that tells us that x is not likely to be much bigger than its expectation. And that thing that tells us is called Markov's inequality. Maybe I should write it. Okay, I'll write it again later. What does Markov's inequality say? It says the probability that x is at least t is at most the expectation of x divided by t. This is true for any random variable which only takes non-negative values. Okay? It's not allowed to be negative ever. All our random variables count things, so they're always non-negative. And what is the proof of this? The proof of this is very simple. Let's prove it. I'm going to prove it here. Expectation of x. What's the definition of the average? It's the sum from k equals 0 to infinity of k times the probability that x equals k. Right? That is the definition of the average. Okay, who can now prove Markov's inequality? Need one more line. I want this to be at least something. Don't be shy. Exactly. Just throw away everything below t. Okay, throw stuff away. This is always positive. And exchange the k for a t. Oops. Right? K is bigger than t, so this also got smaller. But now this is exactly t times the probability x is at least t. Right? Which is what we wanted. Everyone happy? There's not enough smiling. You should be happy with how unbelievably simple this proof is, given how useful this inequality is. Right? Okay. Okay, maybe I'll come over here. Okay. So now what? The probability that x is at least n over 2 is at most the expectation of x divided by n over 2, which is at most, so expectation of x is p cubed n cubed. So it's at most, up to some constant factor, constant p cubed n squared. Sorry, I'm going to, so this means up to a constant factor. Right? The constant factor is less than 1, right? So I can just put less than. It's okay? I just plugged in Markov's inequality with t equals n over 2 and the calculation of the expectation. Okay. So this thing is less than a half if, right, so p cubed, n cubed is less than a half. So we can take p to be less than n to the minus 2/3. Okay. Why are we now happy? Because if, what is n to the minus 2/3? It's log k over k. Right? That's how we chose it. And if p is log k over k, I mean, log n and log k are the same up to constant factor. That's a constant. I said I was cheating a little bit here, and there's a constant in here. Maybe it's like 8 or something, whatever. Now suddenly, our p is big enough. We can choose p to be n to the minus 2/3. And suddenly this is true. And also, this is true. So we've shown that with positive probability, actually with high probability, GMP has no independent set of size k and has at most n over 2 triangles. Okay. So what have we shown? Probability that x is at most n over 2, and independent set, we'll say, and y equals 0 is positive. Right? We'll call it yk. Right? Okay, so how do we finish? Are we just done? If you're a tiny bit careful, this is just a statement about probability. What it tells us is that there exists a graph G on n vertices. Independence number is less than k, and number of triangles is at most n over 2. That's what we've shown. There exists a graph with these properties. And now we can use the idea of removing one vertex from each triangle. What are we left with? We're left with a graph with n over 2 vertices at least, independence number at most k, and no triangles. And so, losing in a factor of 2, we're done. Okay, let's let it sink in a tiny bit. Okay, so what did we do? We tried to just take a random object that had the properties we wanted. It failed. But then we changed the properties we wanted to something a little bit weaker, so it became likely, and it was close enough that then we could then fix the random object, the object we found, at the end. This is called the method of alteration. How are we doing for time, by the way? 20 minutes. Okay. Let's have a corollary of this. There exist triangle-free graphs with arbitrarily large chromatic number. Okay, so how do you construct a graph with large chromatic number? Well, you can stick a clique in it. Right? That's an easy way. There's a clique of size k, chromatic number is at least k. Okay, well, suppose you don't allow your enemy to do that. They have to do it without creating a triangle. Can they still do it? This was first, we first asked even by Tut, who came up with a very clever recursive construction to do it. There's also a clever construction by Zhikov and various other people. But here, we prove it without being clever. Right? So why does this follow from Erdős's bound on R3K? Why does this follow from what we just proved? It's better than chalk. We want a lower bound on the chromatic number of a graph. what lower bounds do you know on the chromatic number of a graph? One is the clique number. Okay, not that one. Exactly. There was at least n over alpha. And why is this true? Why is this true? Don't be shy. Yeah, exactly. So take a coloring with chi of G colors. These are all independent sets, right? So, the size at most, alpha of G. But these guys cover the vertex set. So, alpha of G times chi of G has to be at least n. Right? Leticia had this in her talk, right? She mentioned that. Okay, but now we're done. Why are we done? No, no, no. Nothing complicated.
Okay.
Yeah.
I think it's possible to.
To do what, sorry?
Porque, can I say?
Sure, of course.
Se nós fizermos a operação join, nós vamos ter cliques maiores, pegando os cliques de cada uma dessas partes. E me parece que vai ser a soma, o tamanho dos cliques vai ser a soma, a ordem do clique maior vai ser a soma dos cliques de cada parte.
So, but why does that prove the corollary? So what I want to say is, what I'm trying to say is, this theorem implies this theorem. And I claim that all we need to observe is this is true. And then we're done. And I'm asking why. Right? So this was just the picture. Each color class has size at most alpha. So therefore, alpha of G times chi of G must be at least n. We have to cover all the vertices. So we have this inequality.
I'm sorry. I think, eu acho que eu estava pensando de uma forma diferente do contexto probabilístico. Sorry.
Yeah, sorry. There are many ways to prove this corollary. Sorry, this corollary without using R3K. But yeah, so you can construct these things in lots of ways, but you need to be clever. I don't want to be clever. I just want to say this implies it immediately. But why?
Because you know it doesn't have an independent set of size.
Exactly. So this inequality says exactly there exists a triangle-free graph with no independent set of size bigger than n to the 2/3, basically. But if the independent set of size n to the 2/3, then the chromatic number is at least n to the 1/3. Right? So you're done. So apply to the graph, the triangle-free graph, given by R3K is at least k to the 3/2, implies chromatic number is at least n over k, which is like n to the 1/3. Good. So you have a huge chromatic number. Yeah, and I think all the deterministic instructions give much worse bounds than this on the chromatic number. Yeah. Right, I only have 15 minutes left, so I have to choose carefully. Okay, I think I'm going to give you an application of the second moment method. So I should say, Hoy in his talk this morning mentioned the first moment. He was saying that he was talking about first moment obstructions. This is the first moment. The first moment is the expectation. So it's obstructions like calculate expectation and use Markov. Okay. Oops. So I want to tell you, before finishing today, about what happens when, I'm not sure what the best application to give is. Yes, maybe I'll do it with this. Actually, no, given we've come this far, let's just solve this problem. So theorem, the probability there's a triangle in GMP tends to 0 if P is much smaller than 1 over n, and tends to 1 if P is much bigger than 1 over n. Okay. Which of these two have we already proved? Sorry. Yeah, I should say this less than means tends to 0. So I should say perhaps this is the same thing as Pn tends to 0, and this is the same thing as Pn tends to infinity. Right? So I want to say P greater than 1 over n means P times n tends to infinity. Right? It's bigger by some increasing factor. Yeah, maybe I'll put it back because I want to use this notation more. Okay, which of these two bounds have we already proved? The first one, right? What was the proof? Exactly. So if x is the number of triangles, the probability that the triangle is equal to the probability that x is at least 1 is at most, by Markov, the expectation of x, which equals p cubed n choose 3. And if p is much smaller than 1 over n, this tends to 0 as n tends to infinity. Right? This is just the same as this, defining x to be the number of triangles. This is Markov, with t equals 1. This is, we calculate expectation, and this is just saying, this is p cubed n cubed. If p times n tends to 0, then p cubed n cubed tends to 0. It's okay? Okay. Again, not as much smiling as I was hoping, but we'll see. Okay. Now, how do we prove the second one? So we want to show, so if p is much bigger than 1 over n, the expectation of x tends to infinity. So the expected number of triangles is very large. Does that mean we have a triangle with high probability? Is it true that if the average of a random variable is large, then the random variable is non-zero most of the time? This we're not going to, is it? Sorry. probably epsilon, whatever. Right? The expectation of this random variable is epsilon times n. And n can be as big as you like. Right? But almost all the time it's 0. Right? So it's not enough. Expectation of x tends to infinity does not imply probability of x is strictly greater than 0 tends to 1. Right? Even for non-negative random variables. Okay? So we need more information. We need to show that the x we have over there is not this horrible one here. Right? It doesn't look like this. It behaves nicely. How can we do that? Look at the variance, exactly. So, what is the variance? The variance of a random variable is the average of the square of the difference of x from its expectation. And we have a very useful inequality called Chebyshev's inequality, which allows us to bound the probability that x differs from its expectation by a large amount. It's the variance divided by t squared. Proof. How do you prove this? Hint, it's one line. Thank you. We just apply Markov to the square, exactly. Right? Let's call this y maybe. What do we get? So the probability that the probability that x minus expectation of x squared is at least t squared, which is the same thing as this, right? Just square both sides, equals the probability that y is at least t squared, which is at most, by Markov, the expectation of y over t squared. And the expectation of y is exactly the variance of x. Good. Okay, so this was extremely simple. Okay. Yeah. Proof of Markov was here, and the proof of Chebyshev is just apply Markov. Okay. So, can I raise? Okay, right? Okay, so we need to bound the variance of x. Okay, so how do you bound the variance of x? So let's first observe, let's multiply out this square and use linearity of expectation. Expectation of x squared minus 2x expectation of x plus expectation of x squared. Okay, just multiply it out. Now, linearity, this is expectation of x squared minus constant, constant expectation of x, twice expectation of x squared. And this is a constant. There's minus 2 of that plus 1 of that. So it's just expectation of x squared minus expectation of x squared. Okay? Everyone happy, I hope? Let me erase. What do I want to erase? Yeah, I'll do it over here. No, actually, I'm going to erase. Sorry. I'm going to keep this there. Okay. So, this we know. We have to calculate this thing. So, how do we calculate the expectation of x squared? Where x is the number of triangles in GMP. Well, remember that x is the sum over all triangles of the indicator function that s is in GMP. Right? Counting triangles in GMP. So what's x squared? We just take this and square it. We get the sum over s and t are triangles of the indicator function that s and t are both in GMP. So the expectation is just the sum of the probability of this. It's the sum over s and t are both triangles of the probability that s and t are both contained in GMP. Right? Okay, now what is this? Well, it depends, right? What do the triangles look like? The triangles could be the same. They could share an edge. They could share a vertex. Or they could be completely disjoint. Okay, and what are the probabilities in the four cases? Well, there's 3 edges, so p cubed. Here there's 5, and in both of these cases, there's 6. So we just need to count how many there are of each possibility. And the nice thing about this last one is the number of choices is at most n choose 3 for the first triangle and n choose 3 for the second. So what do we get? We get n choose 3 squared times p to the 6. It's exactly expectation squared. This is exactly expectation. We just need to add on this one. Okay, so this is at most, I'm going to put this over there, sorry. By the way, it's at most expectation of x squared plus expectation of x plus, so there were these, and there were these, and these. So if you add on these, there's 1, 2, 3, 4 vertices. So it's n to the 4, p to the 5. Okay, and I've run out of time, so to say very quickly, I want to claim that this is much smaller than, sorry. What's the variance? It's this minus this. So it's this. This is our bound on the variance. And I want to claim this is much smaller than the expectation of x squared. Why is that true? Well, this is smaller than this because the expectation tends to infinity. And this is much smaller than this because this is like n to the 6 p to the 6. So it's this times Pn squared, and P is like 1 over n. Okay? So it's very easy to see that this thing is much bigger than these two. So what have we shown? We've shown that the variance of x is much smaller than the expectation squared. And what does that mean? That means in this inequality, we can set t to be, say, the expectation of x over 2, and the right-hand side will tend to 0. So proving that the variance is much smaller than expectation squared is enough to tell us that with high probability, x is within a factor of 2 of its expectation. We've shown its expectation tends to infinity, so also the number of triangles tends to infinity. Okay? This is called the second moment method. Okay, so we've run out of time. So I hope all that was reasonably clear. You now should be at the point where you can do most of the first, say, 15 exercises. They're not supposed to be super easy, so don't expect them to be, but hopefully they're now doable. Yeah, maybe, I don't know, talk amongst yourselves and to other people. Let them know how hard you're finding the course. If you're too shy to talk to me, you can talk to other people and they can tell me, and then we'll figure out how fast to go next time. Okay? I have lots of student spies, so talk to them and they'll let me know. Okay? So, yeah, please.
Where's the column set?
They should have been emailed to you.